That is something a programmer shouldn't have to do themselves. You should not have to babysit all that. It's no wonder C has so many memory issues. When I made the video the other day about how I'm going to make a new low-level language instead of writing the high-level intent language Jofito, I found that C is problematic in several ways. So I'm just going to write a new low-level language first, basically build it on a solid foundation. A lot of people seemed to take almost offense at me suggesting this. They said, for example, why don't you use D? Or better C, or C3, or this language already does what you're talking about, or that language already does it. And it kind of boils down to the fact that the vast majority of languages are actually just C, plus we changed X and added Y. And that's all that they are. They still use C interfaces, they still try to do things in the C way, but, we'll put a little twist on it. It's kind of like, it's like if you had, let's say, a bottle of wine that you made, and, one of these is a Pinot Noir, and one of these is a Cabernet Sauvignon, okay, but they're both just red wines. They're different flavors of the same red wine. So when I show up and I'm like, I want a Riesling, that's not a red wine. They are very different purposes. They do different things under the hood. I don't know if a wine analogy was the best way to get that across, but most existing languages do not do what I'm talking about doing. My goal with any language I write is to be a force multiplier language. Rather than be a language that attempts to, for example, like Rust uses bureaucracy to bully programmers into writing safe code, I think that writing safe code should just be what the language naturally makes you flow into doing. That writing unsafe code should be something that's not the easy way. If you choose the hard way, the dangerous way, you make it harder on yourself, but you also make it harder, or you're treading into dangerous territory, and you need to know that and be aware of that. I would not want to write any programming language that doesn't respect the machine under the hood. And modern machines are very, very different. They lie to you. They run parallel, dynamic recompiled execution under the hood. Literally, like the Ryzen 9 chips might have several different execution ports that can do several different tasks at the exact same time. And when you issue a stream of assembly instructions, that chip is actually actively rewriting those into micro opcodes for the built-in parallel very long instruction word processor that's actually running at the core of that chip. The reason that instructions can complete in so-called less than one cycle is because that's in the aggregate. It's not actually less than one cycle. It's that if you have, say, 2 integer execution ports and 2 load store execution ports, you can be fetching the results or fetching the operands for the next set of assembly instructions from the cache at the same time that you're doing the previous set of assembly instructions. So you can be doing math for one thing, and it'll do 2 at a time. You'll write it, A plus B equals C, or whatever. C equals A plus B, F equals D plus E, whatever. And it'll be doing those at the same time. It can literally be pipelining all 4 instructions at once. And most compilers and languages even are not designed to play nice with this. They're designed for a flat memory model with a linear execution sort of programmer mental model is what I'm trying to say. And that's not how CPUs work anymore. They are actively trying to speed up your mediocre assembly under the hood, and they do it different ways. For example, an Intel Celeron or an AMD A-series APU may be starved of execution units. It may be out of order, but it may have a very shallow, stupid branch predictor that gets fooled easily. So what happens is when you write a loop manually, you may not even realize the way you wrote your loop that your if, whatever counter equals this value, then exit the loop manually. You may not realize that the way that you wrote it or the context around it or the way the compiler reinterprets it into assembly code is actually causing the branch predictor on your processor to make a misprediction more often and stall out and force a pipeline flush, which means not just the instruction that you've been working on, but several cycles worth of instructions get thrown straight in the trash. Like the work gets thrown away and redone. And you won't even know this is happening. Likewise, if you have a processor starved of execution ports, you might think, for example, that hand rolling some assembly code that uses all the registers, all 15 or 16 or whatever general purpose registers on your x86 64 chip, that'll be faster because I'm using all the registers. That's not how registers work. Inside, it actually has this register renaming functionality going on. I think they actually call it register coloring, but that could be the compiler side. I get the terminology confused every once in a while. But the processor actually allocates internally things to internal registers differently than what you lay out. And if the chip is a low power, if it's designed for low power instead of high performance, it may be low on execution units. It may not have as many internal registers to shuffle things in and out of. By using all of the general purpose registers, you may think that, this should run faster because I'm using all the registers instead of hitting the cache or the RAM or whatever. But in reality, you may be triggering starvation of the internal renaming of registers inside that VLIW execution core. These things are complex, and every chip is different. And one of the goals of my low-level language is to go, we're not in the 70s anymore. We're not in the 80s anymore. This is not a 6502. We don't have, we don't have a two-cycle increment, fetch and execute instruction. We don't have three-cycle, load whatever from whatever zero page address. That kind of cycle counting stuff doesn't work anymore. That's not how chips work anymore. And the details of every chip, scheduling for the number of execution units and being as friendly as possible to the branch predictor. Basically, you want to minimize pipeline stalls, but C and Rust and Zig and all the other goofy languages that exist right now, they pretend like this is not the nature of processors. They pretend like processors are still fundamentally flat memory model, linear execution mental model. That's not how things work anymore. So the goal is to bring the intent concept, instead of writing the high-level intent-based language first, I write a low-level intent-based language first. But it's not intent in the same way as Jofito was going to be. And I say was because I've stalled that now because I need the low-level foundation first. It is intent as in you don't go, for integer I equals 0, and while, I is less than 100, I plus plus, and then let that run in a loop with manual exit conditions or whatever, because you're telling the processor or the compiler or whatever how to perform the task. You're not telling it what the task is. And because of that divergence, because your intentions were thrown in the trash in favor of strict procedure, something closer to assembly language, but not quite, there's no way to optimize what you were trying to accomplish based on what you're sitting on top of without, look into like how long it took GCC to do graphite optimizations, stuff, just the amount of work that's been done to convert. This is the hen-pecking little procedure, set this integer to this, and then do this condition check at the end of the loop, and then do this operation at every iteration. That's all fine and great, but that doesn't tell the compiler what you were trying to accomplish. It tells it, here is a loop construct And here are the instructions to execute, and that's the end of it. Sorry, I'm holding a phone. It sucks. What I envision is a language where instead of just being like, here's all the really low-level raw, like pointer, offset, counter, blah, 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 the programmer shouldn't have to do that. You just shouldn't have to. You shouldn't have to sit there and peck out for loop with manual exit condition and whatever. You shouldn't have to do all of that manually. And if you do create something like a for loop or, some kind of manual exit or something that you might need to go back to or whatever, it should be something that the compiler is aware of, not just like, well, if this pointer value matches this character, then store that pointer value in pointer Q and then start doing comparisons back to pointer P or whatever. And as long as it matches, see, you should be able to tell the compiler, this is what I'm trying to do. I'm trying to find this character somewhere in this array or this substring or whatever, somewhere in this array. And that's when I match on it, I want to do this with that. For example, I want to copy that, or I want to truncate the string or whatever. Instead of going, okay, so here's how you do it. You do this number here and you increment this number, this amount, and then you do this comparison. No, you shouldn't have to do all that. You should be able to tell the compiler, this is what I'm going for. And the compiler figures out the best way to do that. Because what this opens up is a whole category of optimizations where you can build code, and this is one of the reasons I want to throw out standard issue C, calling conventions and binary formats and all that you're used to on Linux in particular, because what I envision is a system where the compiler builds multiple versions, basically multiple scheduled versions of the code at once, and puts it all in one binary, but builds for several different categories of platform. You have perhaps a ultra low voltage or low power weak CPU variant, and then a strong CPU variant. If a CPU can support, for example, AVX 512, perhaps there's a variant for that. And when you load the binary, the loader for this language's binaries would dynamically basically throw out or only load the components that fit the processor type or category or feature set or whatever that you definitely have, and it only runs that code. As is my luck, a phone call came in the middle of me recording. Anyway, I probably have said enough, but I think I've kind of gotten across some of what I was trying to regarding the new language ideas. One of the most important things about this is if you can say, for example, I'm trying to do a substring search or memory compare, whatever, the language itself can determine whether or not that's vectorizable. But if you're just, picking at pointers, the aliasing nightmare prevents that from happening in a lot of cases. This is why I don't want to keep the legacy of old languages around. A clean sheet implementation is what is needed. And the reason that nobody does this is A, making a programming language is hard enough. B, making a compiler is even harder. And C, when you challenge the status quo in any way, you'll have what my comment section looked like in the last one. Why don't you just use all the stuff we've already come up with over the last 50 years? Well, that's a good question. Why reinvent the wheel? Your wheels were invented for a time when there was no rain on the track, so you just use slicks. But now I need to invent wheels with tread so that it can push the water off the track so that you stop steering into a wall and having to reset. That's my analogy for your pipeline flush problem. And that's what I'm talking about. Modern hardware works so differently that it's constantly dumping all of this work. And the problem is not the hardware. The problem is the hardware is trying to run decades worth of old school language stuff, single tasking language stuff. And we're still writing in the same languages and the same paradigms that got processors to where they are, where they're massive workaround machines in the first place. The first step is get the languages to where they're no longer having to, put processors in a bind where they have to work around your own work. And no, the solution is not to use friggin' intrinsics. That's basically assembly programming. And no, the solution is not to transpile to C, because then you're still outputting C. You're adopting all the negatives of C, and anything good you do in your language is screwed, because, well, guess what? It's still C at the end of the day. You're actually making the task harder. No, if you make it simpler and more sympathetic to the actual mechanics of the machine, then what happens is the machine itself can recognize, oh, hey, this branch is never taken, so I'll always predict the fast path, the happy path, the good path. Or the compiler can recognize the computer supports AVX2, and this is an array operation that the programmer has said we might be doing very long, sparse searches that fail most of the time. So we optimize for that by doing huge AVX scans, and then we cherry pick at the byte level once the AVX scans have reached the limit of what they can do, or we hit an alignment issue or whatever. But things like alignment issues or vectorization, that is something a programmer shouldn't have to do themselves. You should not have to babysit all that. It's no wonder C has so many memory issues, given how goddamn hard they make it to do something that should be simple, like SIMD. Anyway, that's enough from me. I'm going to go in this storage unit and hope the sun doesn't come out again, because God almighty, it's hot in North Carolina. Thanks for listening. Take care. That was fucking stupid.